Right. I will welcome you back to this lesson. And in this lesson, we are going to look at determination of composition of the distillate obtained by steam distillation. So here, as I told you that we're going to specifically be looking at calculations, we are going to specifically look at some of the questions that involve calculations of mixtures separated by steam distillation. And allow me derive something here. So we are going to say, if we consider a distillate, assuming that after our distillation, we've got a distillate containing liquid air and water. Now, you're going to let the vapor pressure exerted by air to be PA and mole fraction of air in the distillate to be XA. Now, remember the composition is determined from the exerted vapor pressure. And therefore, we are going to use Dalton's law. All right. Now, from Dalton's law, we know that partial pressure of A is going to be equal to small fraction times the total. And call this one equation 1. And for water is going to be mole fraction of water times the P total. But looking at these two equations, if we get equation 1 and we divide it by 2, if you get equation 1 and you divide it by 2, you're going to have PA over P water is equals to XA over X water, because the P totals are going to cancel. But remember, mole fraction of A is equal to the number of moles of A divided by the total number of moles of A plus the number of moles of water, and also the mole fraction of water is equals to number of moles of water out of the total for A and then for water. Looking at this, we can plug this one into this, and thus we shall have our PA over P water equaling to, where XA is, we shall put this, where X water is, we shall put this. So it is going to be NA out of NA plus NA water divided by the one of water. So even if we multiply a reciprocal, NA plus NA water out of any water. These moles will cancel, and we shall have PA out of P water equaling to number of moles of A out of number of moles of water. So after having gotten this, these partial pressures, either you can look for NA depending on the question, but then we know how we can get number of moles of A. Number of moles of A is equals to mass of A over the relative formula mass of A, right? And number of moles of water will be equal to mass of water out of the relative formula mass of water, implying that the overall thing now, by getting this Na and N water, we put it here, we shall have that Pa over P water is going to be equal to number of moles of A, which is mass of A, it is the number of moles of A, which is the mass of A over relative formula mass. Then we divide by mass of water over relative formula mass of water, of which after taking the reciprocal, we shall have mass of water times the relative formula mass of water, and here times relative formula mass of A. So we shall end up by saying that mass of A over mass of water is equal to vapor pressure of A times the relative formula mass of A I'm making this one the subject of the formula. So meaning I will divide by RFM of water over RFM of A, which will take the reciprocal. A will go up, water will go down. So we shall have partial pressure of water times its relative formula mass. So this is the formula that we shall use. This is the formula that we shall be using to calculate some of the numbers. Let's look at examples and we see how best we can come about the answers. So a mixture examples, number one. A mixture containing a substance R was steam distilled at 760 millimeters of mercury and 98 degrees Celsius. The distillate contained 5% by mass of water the vapor pressure of water is 734 millimeters of mercury at 98 degrees Celsius. Calculate the molar mass of R. So given this, we have been given percentage of water. So we can also get percentage by mass of R. So we shall say percentage by mass of R is going to be equal to 100 minus 85%. So this is going to give us 15% by mass. Now, we have vapor pressure of water and the mixture was steam distilled at 760. So 760 is the total, meaning that I can get vapor pressure of R. It will be 760 minus 734, which is 26 millimeters of mercury. Now I substitute in the formula mass of R, now it will be mass of R, the compound, over mass of water is going to be equal to pressure of R times RFM of R over pressure of water times relative formula mass of water. Mass of R is 15% over mass of water is 85% by mass. So this is going to be equal to partial pressure of R, which is 26, times its relative formula mass. Partial pressure of water is 734 times molecular mass of water, which is 18. Now, this one can get you the answer as RFM of R equals to, we are making RFM the subject, so we shall multiply, we shall cross multiply 734 times 18, then times 15, of course multiply times 15, we shall divide by 26 times 85. This one will give you the RFM. From my calculator, I'm getting 89.67. So that is what we are having. That is what we are having. Example 2. Let's do example 2, and we see a mixture of naphthalene, which is C8, sorry, C10, H8, and water distills, not boils, distills at 98.3 degrees Celsius and 753 millimeters of mercury. Calculate the percentage by mass of naphthalene in the distillate naphthalene in the distillate. They have given us vapor pressure of water at 98.3 degrees Celsius as 715 millimeters of mercury. We have been given carbon as 12 and hydrogen as 1. Now, for this case, they have said that a mixture of naphthalene and water distills, meaning they first form an immiscible mixture, then they distill at 98.3 and that pressure of 753. So the mixture distills at this temperature and at this pressure. Calculate the percentage by mass, but they gave us vapor pressure of water. Now they want us to calculate the percentage by mass of naphthalene. So allow me say that let percentage by mass of naphthalene be say X%, meaning that the one of water is going to be 100 minus X%. All right? Yes. Then, since we know the compounds, can look for the molar masses. So molar mass of naphthalene is going to be carbon 12 times 10 and hydrogen 1 times 8. This is going to be 128. And we know the one of water is just 1 times 2 plus the 16, which comes to 18. These are molar masses. We've been given the vapor pressure of water as 715, and therefore we can get the vapor pressure of naphthalene by getting the one at which the mixture distills, 753, minus the one of water, 715. And this one will give us 38 millimeters of mercury. We substitute in the equation, which is mass of naphthalene out of mass of water is going to be equal to vapor pressure of naphthalene times its relative formula mass. We divide by vapor pressure of water times relative formula mass of water. Substituting in the formula mass of naphthalene, we called it X. The one of water, we called it 100 minus X. This is going to be equal to partial pressure of naphthalene, 38, times its molecular mass. Its molecular mass, we say that this is 128 over partial pressure of water, 715, times relative formula mass, 18. So we shall have, if we cross multiply, we shall have 715 times 18 is 1,280. Shall have 1,280. X is going to be equal to 38 times 128 is 4,864 into 100 minus X. Interestingly, solving will give you the value of X as first open brackets. So we shall have 1,280. X is equal to 4,864,000 minus 4,864X. This one will give you the value of X as 27.3. But the question is, capture the percentage by mass of naphthalene. So we shall say, therefore, the percentage by mass of naphthalene is equals to 27.43%. And that is the answer. Well, I'm going to do another example. And this example is a bit lengthy. It's my example 3. And it goes that when An organic compound Y containing carbon and hydrogen was burnt in excess oxygen, 31.5 grams of carbon dioxide and 10.7 grams of water were formed. Calculate the empirical formula of Y. Then B, Y was steam distilled at 70 degrees Celsius and 760 millimeters of mercury. And the distillate was found to contain 91.1% of Y. Vapor pressure of water at 70 degrees Celsius is 234 millimeters of mercury. Roman 1, capture the formula mass of Y. Roman 2, deduce the molecular mass, the molecular formula, sorry, of Y. Deduce the molecular formula of Y. For this case, if we are to look at what we are given a compound Y. When burnt, it gave 31.5 grams of carbon dioxide and water. So this one, that information can give us masses of carbon and hydrogen. Mass of carbon will be equaling to 31.5 times 12 out of the total 44. Because you'll be saying that if 44 grams contain 12, what about 31.5? So this one will give you the mass of carbon as 8.60 grams. Then you also look for mass of hydrogen, which will be 10.7. Let's add a 6 so that the question can come very well. 76, then times 2 atoms of hydrogen out of 18. How does it come about? You'll be saying, if 18 grams of water contain 2 grams of hydrogen, what about 10.76? So this is going to give you 1.20 grams. Then now, to get the empirical formula, we still remember the steps, right? we need elements, carbon, hydrogen, percentage composition, but this time around we have composition by mass. Composition of carbon is 8.60, while the other is 1.20. After the composition, we can get moles. Moles we divide by the atomic masses over 12, 1.20 over 1. When you divide 8.6 by 12, it's 0.717, 1.20 here. Now, another thing is to get the ratio, the molar ratio. Need to get the molar ratio. So the molar ratio will be divided by the smallest, 17 over 0.717, 1.20 over 0.717. So here, this one is going to give you 1, and this one is going to give you 1.67. Don't round off this one to 2, but instead look at eliminating it to form a whole number. When it is 1.5, 1.6, we multiply to eliminate it. So this one we multiply by 3. And multiply it by 3, it will become 5, while this one will become 3. So the molar ratio is 3 to 5. Now, after this, we can deduce and say that the empirical formula is carbons are 3, hydrogens are 5. So that is what we get as our empirical formula. Then going to part B, they are saying that when Y was steam distilled at this and 760, so this is the mixture. So if steam distilled at 70 degrees and 760 millimeters of mercury, the distillate was found to contain 91 of Y. So meaning that if it contains 91 of Y, we can get a percentage of water. And if the vapor pressure of water is 234, we can get the vapor pressure of Y. And then we get the formula mass from which we can determine the molecular formula. So now here, we shall need to first get the percentage of water. Will be equaling to 100 percentage by mass. Be equaling to 100 minus the percentage of the other, 91.1. And this is giving 8.9%. Then we also have to get the vapor pressure of Y. Vapor pressure of Y would be the total 760 minus the one of water, 234. So it will be 526 millimeters of mercury. Then now we substitute into the formula. It will be mass of Y over mass of water is equals to vapor pressure of Y times relative formula mass of Y over vapor pressure of water times the relative formula mass of water. Excellent. Mass of Y, percentage 91.1 out of mass of water 8.9. This is equal to vapor pressure of Y 526 times relative molecular mass of Y. We don't know it, over Vapor pressure of water, we got it as 234 and the molecular mass of water, which is 18. Cross multiply and get the relative formula mass of Y. So the relative formula mass of Y is going to be equal to 234 times 18 times 91.1 out of 526 times 8.9. So it is going to be 81.96, which is the same as 82 grams. For this case, you can round off to 82. So that is a relative formula mass or the molecular mass of Y. Now, if we are having the molecular mass, we can do Roman 2, which needs the molecular formula. And the fact that we have the empirical formula, now the molecular formula becomes the easiest to get. So the molecular formula is going to be equal to, rather we shall get it from, by me having C3, is it C3, H5, into N, that one should equate to 82, the molecular mass. So carbon is 12 times 6 plus hydrogen 1 times 5, everything into N, one should give you 82. This is 70. This times 3, right? 36 plus 1, that is 42, 41. 41 N is equals to 82. When you divide by 2, N is going to be equal to 2. When N is 2 and you substitute it here, you're going to get your molecular formula as C multiply 2 here, 6, H multiply 2 here, 10. C6, H10. Someone can easily look at it as cyclohexene. Cyclohexene. Okay. Now, that is what we are having for that particular case. That is what we are having. The final question that I'm going to do for you, it's an analysis question. And after this question, we shall record another video that will be looking at the graphical methods. A of this question is to state the effect on vapor pressure of water and one state the effect on vapor pressure of water and one on the total vapor pressure of the system when small amounts of the following substances are separately added to water at 25 degrees Celsius. We shall have substance added to water then we shall have effect on vapor pressure of, the first thing shall be vapor pressure of water. Then another one shall be on vapor pressure of the system, total vapor pressure of the system. What happens when you add the following substances, which are going to put here, on the vapor pressure of water and then the total vapor pressure of the system? What happens when you add 1 sodium chloride, 2 when you add propanone is CH3COCH3, then 3 when you add what else can cause a change? Tetrachloromethane. Tetrachloromethane, CCl4, tetrachloromethane. Now, they can tell you to, after stating what happens, you explain each of the answers. Now, I want you to know that sodium chloride is a non-volatile solute. In other words, when you're told to explain, you can write as I'm saying. Sodium chloride is non-volatile solute. So when added to water, its particles occupy the water surface and hinder the escaping tendency of water molecules into the vapor phase exerted by water. So the vapor pressure exerted by water is reduced, and consequently, the vapor pressure of the solution is also reduced. So when we add sodium chloride to the solution to water, the effect of evaporation on water reduces, the vapor pressure reduces, and also for the system, it reduces. Because we have said that it is non-volatile, and therefore when added to water, its particles occupy the water surface, and the escaping tendency of water molecules into the vapor phase does what? Reduces, okay? Or is hindered. Now, when the escaping tendency of water into the vapor phase reduces, it means that water, the effect of vapor pressure of water, the vapor pressure of water will also decrease. It will decrease, and generally the whole system. When we add the propanone in water, both are polar because of the differences in electronegativities between carbon and even some hydrogen bonds in water. In other words, for propanone, when you add propanone in water, the pressure increases. Even for the system, it increases. We want to establish the reason as to why. Okay, we are saying that both propanone and water molecules are polar, but hydrogen bonds in water are stronger than the van der Waals forces between propanone molecules. So when the two are mixed together, weaker intermolecular forces are formed between the unlike molecules due to repulsion between similar polarities. And that one will result into the escaping tendency of water molecules from the solution into the vapor phase, hence increasing vapor pressure exerted by both water and water propanone. That is the system. So generally for that case, it increases. So we talk about the molecules being polar for each, but we talk also about the hydrogen bonds in water being stronger than the van der Waals forces holding the propanone molecules together. So in addition, or in mixing these two liquids, the weaker intermolecular forces are formed between unlike molecules due to repulsion between similar polarities. And what happens is there is an increase in escaping tendency of molecules from solution into the vapor phase, thus increasing the vapor pressure exerted by both water and propanone. Okay, then when we add tetrachloromethane, you know, tetrachloromethane and water, they form an immiscible liquid mixture. In other words, tetrachloromethane is miscible with water, meaning that each component of what exerts an independent vapor pressure. All right. Now, meaning that the vapor pressure of water remains constant. So here we say remains constant, because being immiscible, when you mix them, tetrachloromethane being immiscible with water, mixing them will call for each one to exert an individual or independent vapor pressure, meaning that if the vapor pressure of water was 30, it will keep 30, because on addition or on mixing the two, they have exerted vapor pressures independently from each other. So the vapor pressure here remains constant, while for the system, it will increase. Why? Because each component contributes its vapor pressure to sum up the total vapor pressure of the system. Thus, the vapor pressure of the system increases. So they can ask you to state, and then after you explain. So in explanation, you can write whatever I have been talking about. Let's meet in another video. We catch up, as I'm going to record about how we work, or how we go about the question that involves graph work. See you there.